In 5.2, we're going to be proving trig identities. Okay. I want to just remind you, the payoff of trig identities is that they give us options. So I can write a trig expression this way, or I can write it that way. Now in this class, we're just practicing doing that. So it sometimes is easy to make it feel like it's just kind of pointless or it's just a puzzle and why are we doing this? Now I like puzzles, so I'm okay with that. If you want a good payoff for why are we doing this, you got to stay through this class and pre-calculus and get to calculus. In calculus, there are going to be times when you want to do calculus things to a trig expression. And when it's written this way, it's really hard. And when it's written that way, it's really easy. Okay? So using your trig identities to go from writing it the way that makes the problem hard to writing it the way that makes the problem easy, you get a big payoff because you get to go from a hard problem to an easy problem. Since we don't know calculus yet, we don't really get that payoff. We're just building up our skills so that by the time you get to calculus, you'll be able to do that. So there is a reason behind doing this, but it feels like it's just a lot of practice rewriting things different ways, and it is, but it's practicing for a good reason. Okay. Now, before we actually talk about proving trig identities, I want to just review some of the algebra skills that we're going to be using in doing that, and review that in the context of trig. So for example, if I have sine of theta over cosine of theta plus 2 over cosine squared theta. So that's two different fractions. Sometimes it's going to be simpler to have just one fraction. Other times it's going to be simpler to take one big fraction and break it apart into smaller pieces. Okay? Right now, I want to just practice the skill of, hey, if I have two fractions, how do I combine them to get just one? So when I'm working with fractions, I know I would need a common denominator. So here my denominator is cosine of theta. Here it's cosine squared, which is 2 factors of cosine theta. Okay. So this denominator divides evenly into this denominator. I can get to this one by multiplying that one just by cosine. So I'm going to say my LCD, my least common denominator, is cosine squared theta. This already has that, so I don't need to change it. This I would multiply by 1 in the form of cosine theta over cosine theta to get to that denominator. So then I would have cosine theta sine theta over cosine squared theta plus 2 over cosine squared theta. And once the denominator is the same, you can add and the denominator does not change. If you think about it, if I was adding goats to goats, I would just get more goats. If I'm adding halves to halves, I'm going to get more halves. If I'm adding thirds to thirds, I'm going to get more thirds. The denominator tells me what type of thing I have. Here the type of thing I have is cosine squared. So I've got this many plus that many. I've got a total of cosine theta sine theta plus 2. Now, is it always going to be simpler to have one fraction versus 2? No. But if I thought for a particular problem it was, this is how I would get there. All right, let's try another example. So let's suppose I have 1 over 1 minus cosine theta minus 2 over 1 plus cosine theta. Okay. So here my two denominators are 1 plus cosine theta and 1 minus cosine theta. Looks like they have a lot in common, but they don't have any factors in common. Factors are things that are connected by multiplication and division. And the least common denominator has to be a multiple of both denominators. So the fact that I've got ones and cosines doesn't really help me because they're not connected by multiplication. They're connected by addition and subtraction. So here, my least common denominator is just going to be the product of the two denominators. When they have no factors in common, we just multiply them out. So if I want to get to that common denominator, here I already have that first factor, so I would multiply by 1 in the form of 1 plus cosine theta over 1 plus cosine theta. Here I already have the second factor, So I would multiply this by 1 in the form of 1 minus cosine theta over 1 minus cosine theta. So now I'm going to get here 1 plus cosine theta over 1 plus cosine theta times 1 minus cosine theta minus, I'm going to just distribute that 2. So I'm going to get 2 minus 2 cosine theta all over 1 plus cosine theta, 1 minus cosine theta. This negative sign, this subtraction sign, applies to the entire fraction. So I'm careful to keep it in front of the entire fraction, not just associate it with just the 2. Okay. All right, so in the next step, I'm going to do 2 things. Okay. So first of all, once I have a common denominator, I just add or subtract the tops. So here I'm subtracting, so it's 1 plus cosine theta minus, in parentheses, the top here. That negative sign applies to the entire fraction, so I'm going to apply it to the entire top of that fraction. So in my next step, I'm going to need to distribute that negative. Then on bottom, I've got this common denominator, but I'd kind of like to have it multiplied out. Since it's 2 terms times 2 terms, I'm going to FOIL. So I'm going to get, first terms give me 1. Outsides give me minus cosine theta. Insides give me plus cosine theta. And last terms give me minus cosine squared theta. Outsides and insides are exact opposites, so it's kind of nice they cancel. Now that'll happen anytime your 2 factors have the same 2 terms, 1 and cosine theta, but connected with opposite signs. Okay. If you don't have that, the outsides and insides won't cancel. Okay. If you recognize that you have that here and you go right to 1 minus cosine squared theta, I'm totally fine with that. Okay. All right. So now I'm going to distribute that negative. So this is going to become 1 plus cosine theta minus 2 plus 2 cosine theta all over 1 minus cosine squared theta. And then in my last step, I can just combine some like terms. So the 1 minus 2 is going to give me a negative 1. That's 1 copy of cosine plus 2 more, so I've got plus 3 cosine theta. And if I want to, I could write that using my Pythagorean identity as sine squared of theta. Okay. Now, for this problem, if I had just said subtract to get 1 fraction, and you left the denominator as 1 minus cosine squared, that is totally fine. Okay. I think it's a little bit simpler to switch it to sine squared, so I went ahead and did that. When we're proving identities, we're going to have a particular goal in mind. We're going to want to simplify until we get this specific expression, so we'll know when to stop. When we're just practicing our algebra skills, often there's going to be more than one acceptable place where you could stop and have followed the directions that I gave you. Okay, so that's 2 examples of taking 2 fractions and combining them by adding or subtracting to get just a single fraction. And there are going to be times when that's going to be simplest. Now there are other times when it's going to be simpler to take one big fraction and split it up into 2 smaller fractions. So let's say I've got sine theta plus cosine theta over sine theta. Now often people will see, ooh, sine theta on top and on bottom, and try to cancel. No, we cannot do that as long as that sine theta is connected to the rest of the top by addition or subtraction. That's called canceling over addition and subtraction, and it is just plain wrong. Let me show you why. Let's say I had 2 plus 5 over 2. Hopefully we can all agree that that is 7/2. That is correct. Notice, if I try to cancel the 2's, sometimes people say they just disappear and they're left with 5. Other times people would say, oh, it cancels and that becomes a 1 and you get 6. But the correct answer is neither 5 nor 6. Okay, so I can't cancel when I've got something connected with addition and subtraction. And if you're not sure whether you can do something, giving yourself a similar example with just simple numbers can often help you to figure out whether that's something that's legal or not. What I can do is I can distribute the division. Okay. So this whole thing is being divided by sine theta. Division distributes just like multiplication does. So I can say this is sine theta over sine theta plus cosine theta over sine theta. Now I can say that that's 1 because I'm not adding or subtracting anything to the sine theta that's on top. And if I want to, I can say that that's cotangent of theta. Again, for the purpose of, if the direction said distribute the division and write as a sum of 2 terms, if you kept this as cosine over sine, that would be totally fine. I think it's simpler to switch it over to cotangent. So it's very nice when the denominator contains just 1 term. Sometimes distributing that division allows you to simplify the individual terms, and so that can be simpler. Now, if I had something like 2 plus sine theta over sine theta plus cosine theta, here distributing the division isn't going to help because the entire thing is being divided by this. I could distribute the division, but it becomes this. I don't think that's any simpler. So distributing the division to break one big fraction into smaller pieces tends to be useful when you have just 1 term in the denominator. If you have addition or subtraction in the denominator, generally speaking, it's not going to be particularly useful. Not wrong, just probably not useful to split that up into 2 pieces. So that's something to keep in mind. And so now we have reviewed how to take 2 fractions and combine them into 1, and how sometimes we can take one big fraction and break it up into smaller pieces. And what's going to be beneficial is going to vary depending on the circumstances. Sometimes it's nicer to just have one thing. Other times it's nicer just to have a bunch of little things. Okay. So we want to practice both of those skills. All right, next video we'll review a little bit more algebra, and then we'll be ready to move on and actually start using that algebra to prove some additional identities.